Welcome to the Problemas channel season 2 episode 30, the episode which I titled One Integral, Two Integrals, because in this episode we will use the scope expansion or expand and conquer problem solving approach in order to evaluate the integral shown behind me on the board. Before we do that, however, as a traditional friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section, find the episode titled The Problemas Channel How To. Watch that episode in its entirety and follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E30, we were asked to evaluate an indefinite integral whose integrand has the following structure. It is a product of three functions: an exponential function, the trigonometric function of sine, and the trigonometric function of cosine. The exponential function here has the following shape. It is e, which is the base of the natural logarithm, raised to the power a times x. The trigonometric function of sine has the argument of b times x, and the trigonometric function of cosine has the argument of c times x, and the numbers a, b, and c are constant real numbers, and overall the integration is carried out with respect to the dummy variable x. In this problem, we were asked to evaluate this integral precisely using the scope expansion or expand and conquer problem solving approach. And if you were not able to solve this problem completely correctly and on your own, in order to make this episode slightly more fun, I will be giving out hints to you, and I will be giving you an opportunity to pause this video, walk away, think about the hint, and try to solve the problem from that point onward completely by yourself, as we explained in season 1, episode 2. And here is the very first hint. Within the given integrand, pay a close attention to the structure of this factor over here. It is a product of what? It is a product of two trigonometric functions, each of which is evaluated at, generally speaking, different arguments. The trigonometric function of sine is evaluated at b times x, and the trigonometric function of cosine is evaluated at c times x. Does this formation over here, does this product ring a bell? Think about it. Recall that according to the scope expansion or expand and conquer problem solving approach, if we want to solve this or that technical problem, we perhaps counterintuitively, instead of making a problem narrower, smaller, and simpler in some sense, should try to make that problem seemingly wider, larger, and more complicated. And that is why for many students who are learning about the scope expansion or expand and conquer problem solving approach for the first time, the application of that problem solving approach to the process of solving this or that technical problem may seem difficult and, again, counterintuitive. But this is not the case. Sometimes when we make our temporarily whole problem that we're given at this particular moment a smaller part of yet a bigger whole, then by increasing the scope or increasing the amount of material in which we embed the previous whole, we can gain a tactical advantage or perhaps a different look at our problem, and that different look may give us again a competitive advantage. In this problem, I will begin again writing material on the board if you were not able to solve this problem completely correctly and on your own. And the moment you realize where this is going, we suggest, as we noted in season 1, episode 2, put the video on pause, walk away from the computer, and try to solve this problem on your own from that point onward. That is a way to gain the most benefit from working with the material that we present on this channel. Again, guided by the idea of scope expansion or expand and conquer problem solving approach, we, perhaps counterintuitively at first, will begin increasing the amount of material that we work with initially. As such, forget about the exponent for a moment. Let us write down our factor over here first, like so. So this is the trigonometric function of sine evaluated at the b times x, the argument, times the trigonometric function of cosine evaluated at c times x. That was the hint from the previous segment. If that did not help, then let me do it again. Sine, the trigonometric function of sine evaluated at the argument b times x, times cosine, the trigonometric function of cosine, times evaluated at the argument c times x. So here I wrote the same material twice. We already increased or incremented the amount of material that we're working with. At this point, some of our viewers may think, what Roman is doing, what is going on? Well, there is a method to this madness. Think about this. This is your second hint. Think about it, put this video on pause, walk away, see if this is where this is going. All right, so now next, if that is not helpful, let me write a little bit more stuff over here on the board. So now we write the cosine, the trigonometric function of cosine evaluated at the argument b times x, times the trigonometric function of sine evaluated at the argument c times x. See, right now, we not only doubled, we tripled the amount of material that we work with. And what is next maneuver? See if this helps. If this particular maneuver already helped and you get the sense of where this is going, again, we suggest that you put this video on pause, walk away, try to solve this problem on your own completely and correctly from this point onward. If that did not help, then let's do this experiment again. The trigonometric function of cosine evaluated at the argument b times x times the trigonometric function of sine evaluated at the argument c times x. Look at this right now. Driven by the ideas of the scope expansion problem solving approach, we took our integrand and we quadrupled the amount of material that we're working with. Why in the sane world would we do that? Well, here is the next hint. We put the plus sign over here, we put the minus sign over here. Does that ring any bells? Well, this string of symbols actually collapses into what? The trigonometric function of sine evaluated at what? Because this is a plus sign, that will be b plus c x. So far, so good. And because there is a minus sign over here, this trigonometric monstrosity collapses nicely into what? The trigonometric function of sine evaluated at the argument b minus c times x. You see? And what do we have now? Let's count. 1, 2, 3, 4, 5, 6. Oh my God. We multiplied the amount of material that we had to work with originally sixfold. Does that make any sense? And that is precisely why the application of this scope expansion or expand and conquer problem solving approach at first may seem very difficult or counterintuitive. Why would we increase the amount of material that we have to work with when the natural or psychological tendency for most people is to make things narrower, smaller, and simpler? Here we're ballooning the material. We're making our problem seemingly wider, larger, and more complicated. Well, sometimes it is the case, but sometimes it is not. What do we see over here? Well, let's right now add these two bad puppies together, and if we do, what will happen? Well, if we add these two relations together, then we see that amazingly enough, this summand and this summand will cancel each other. So far, so good. These two guys will double in value, so we will have 2 times something times sine, the trigonometric function of sine evaluated at the argument b times x times the trigonometric function of cosine evaluated at the argument c times x. And this is equal to what? Well, this is equal to the sum of two sines shown over here. So let me leave some room over here. I'll write sine evaluated at b plus c x plus some room sine evaluated at b minus c x. So far, so good. Counterintuitively, perhaps, increase the amount of local material 6 times, write all these wonderful symbols, but then sum the two relations, witness the cancellation of two summands, produce twice the amount of material that we given in the original problem. This is a constant factor 2. We know how to deal with 2. But now look, the tactical advantage that we gain precisely by applying the scope expansion or expand and conquer problem solving approach is the simplification in some sense of the structure of the integrand that we have to deal with. What would be the next maneuver? Think about it, put this video on pause, and if you realize where this is going, proceed on your own. Well, now we introduce our exponential function. We multiply this relation through by this one and the same exponent, e to the power a times x, e to the power a times x. So far, so good. So far, so good. Now we integrate both sides. Integral, integral, integral. We also see dx. I will not write it down, but you see what's going on in your paperwork you do. dx, dx, dx. And now what do we have? Well, if we designate this integral as I, let's say I, this is I, what do we see now? That twice, let me write it this way, twice the integral I is what? Is the sum of two integrals. But now let's look at these two integrals closer together. Let me spell it out more nicely over here. This integral of e to the power a times x times sine of b plus c x dx plus the integral of e to the power ax times sine of b minus c x dx. You see, this is the competitive advantage that was afforded us precisely by the idea of applying the scope expansion or expand and conquer problem solving approach to the original integral. Temporary explosion in the material that we deal with, but then competitive advantage and simplification. In theory, and I am only joking a little halfway, if you're working on your PhD in physics, mathematics, or computer science, whenever you come to this, what will this be called? This will be called reduce and conquer. This is a previously solved problem. This is a typical table, so to speak, integral, and in most calculus books, in the back of the book, the value of this integral will be shown already. You will not have to evaluate this integral. And now we understand where did the title of this episode come from. One integral? No, not really. Two integrals. But each of these integrals is what? Is a table integral, and in its structure, it is actually one and the same integral, because here we have what? This is a constant real number, and this is a constant real number. And each of these two integrals is a previously solved problem. Done, essentially, the problem has been solved precisely by applying the scope expansion problem solving approach. And for the impatient viewers, you can skip the next couple segments. But for curious travelers, I will show again how to apply the scope expansion problem solving approach to the evaluation of these integrals shown over here at the bottom, and we will do it in the next couple of segments. This segment and a couple of segments that will come after this one are optional for curious travelers only. If you're in a hurry, you can skip this and few next segments and fast forward to the answer. But here I will demonstrate again how to apply the scope expansion or expand and conquer problem solving approach to the process of evaluating the integrand whose structure is shown over here. And remember, this is the previously solved problem from our previous segment, where the value of p, where p and q are constant real numbers, is actually a in our original problem, S2E30, and the constant real number q is basically b plus minus c. Again, this is a constant factor in front of the argument x to both the trigonometric function of sine, and that is why we introduced it over here. Okay, so here, instead of playing games and ballooning the material that is given in the integrand of the given integral as we did in the previous segment, here we will execute an even more sinister maneuver. Instead of dealing with one integral, we will deal with two integrals. And the close cousin of this integral is what? Will be a function c that is also somehow depends on the constant numbers p and q. That will be the integral e to the power of p times x times the trigonometric function of cosine evaluated at the argument q times x dx. You see, this is also unnatural for many students who initially begin working with the scope expansion or expand and conquer problem solving approach on the one hand, and also comes as part of tribal knowledge or overall experience working with the integral. Instead of evaluating one integral, we're actually making something that seems totally unnatural. We take on yet another integral and we deal with two integrals. However, again, by expanding the scope of the material that we have to deal with, here is even a more notorious expansion. Instead of one integral, we deal with two. However, precisely because a deeper mathematical connection between the trigonometric function of cosine and sine, sometimes this is actually advantageous. So again, temporarily ballooning the amount of material that we have to deal with allows us to gain a competitive advantage. So how do we gain the competitive advantage? By perhaps counterintuitively expanding the amount of problems that we have to solve. Instead of one, we have to solve two. Well, let's work with the sine, with the function s of p of x and this integral. Here we will move the exponent under the differential over here, and we will rewrite our integral s. I will drop designation p and q. You guys understand what is going on, but here I want to save some space, and I will omit the designations, the designation of the constant p and q, but it is evident that this connection is there. So for the function s, we will have what? 1 over p times the integral of the trigonometric function sine, the trigonometric function of sine evaluated at q times x, d of what? E to the power px That much should be understood by everyone. Essentially, what we're doing here, if I were to say these words, is we're preparing or setting up the integration by parts once. So here we have u dv. So once we spell it out once, what do we have? We have 1 over p e to the power px times sine, the trigonometric function of sine evaluated at q times x, and then what? Minus u du and v, right? So it will be minus q over p integral e to the power px cosine times the trigonometric function of cosine evaluated at the argument q times x dx. That maneuver is again understood by everyone. Integral of u dv equals uv minus integral of v times du. The first differential of the trigonometric function of sine is what? Is the trigonometric function of cosine times the first differential of the argument. Q is a constant multiplicative factor, comes out q over p. Wonderful. Now we do the same thing with the integral c. We have again 1 over p integral of what? This time it will be the cosine, the trigonometric function of cosine, evaluated at the argument q times x d e to the power of p times x. And this will be what? Again, 1 over p e to the power p times x times the trigonometric function of cosine evaluated at the argument q times x. Here minus v du, integral of v du, but minus will cancel out with what? The first differential of the trigonometric function of cosine will be minus sine. Minus times minus will be what? Plus, and the constant multiplicative factor. So dq of x will be what? Q dx. So here we'll have plus q over p integral of e to the power px times the trigonometric function of sine evaluated at the argument qx dx. And now this is where we laugh. This is where we earn our paycheck, or this is where the scope expansion problem solving approach earns its paycheck. Why is that? Let's take a look at these two integrals over here on the far side or on the right side on your screen. What is this integral? This thing right here? This guy matches our original integral c completely. This is c. And what is this? What is this integral? This is precisely our integral s. This is precisely our integral s. So what do we have now? If we omit this and this, I will take a short break right now and erase all this material and write it down nicely so that we will all understand. S is equal to this expression minus q over p times c. And what is c? C, forget this, is this expression plus q over p times s. And what do we have? We have a system of two equations with two unknowns, and the equations are linear in the unknowns, s and c, and voila, we know how to solve such equations. And by doing so, we completely evaluate the original integral, and as an added bonus, yet another integral that we perhaps counterintuitively took on while we were trying to evaluate the original integral. Observe that once we write down the results of our partial integration, then what happens next becomes almost immediately obvious. That is, notice that we have our function s on the right-hand side of the equal sign in the equation that expresses the value of the integral c. And we have also the integral s on the left-hand side of the equal sign that expresses that integral in terms of p and q and the integral c. So what does this suggest? This suggests that if we add these two equations, then there is a chance that s on the right-hand side of the equal sign and s on the left-hand side of the equal sign will what? Will cancel each other out if we, that is, multiply the first equation through by what? By q over p. So if we multiply the first equation through by q over p uniformly, meaning across the left-hand side and the right-hand side, what will we have? Q over p times s. This is exactly the shape of the summand that we have over here. Here we will have q over p squared. And here what we will have? Q squared over p squared. So far so good. I apologize if this 2 is too small for you guys. Probably maybe zoom in on your monitor to see what is going on, but this is basically our integral c has a factor of what? It's a ratio of q squared and p squared. Q is in the numerator and p squared is in the denominator. Now we execute the maneuver that we talked about a second ago. We add or sum these two equations, and what do we get? Well, look at this. Q over p times s on the left-hand side of the equal sign and q over p times s on the right-hand side of the equal sign disappear. On the left-hand side of this equal sign, what do we have? Precisely, we have only c, our integral c. And what do we have? Well, it will be this guy. 1 over p times e to the power p times x times the trigonometric function of cosine evaluated at the argument q times x. It's this guy. Everything is transparent. Plus this guy right here, plus q over p squared times e to the power p times x times the trigonometric function of sine evaluated at the argument q times x minus q squared over p squared times c. And what do we have? We have an equation that is linear in the integral c. So what do? Now we go back to our middle school arithmetic and pretty much solve this straightforward equation for c. So once we carry this guy to the left-hand side of the equal sign, what we will have? We'll have c times, let's write this down, p squared plus q squared over p squared paren equal to what? Equal to this two summands over here. So this will be 1 over p times e to the power p times x times cosine evaluated at q times x plus q over p squared times e to the power p times x times trigonometric function of sine evaluated at the argument q times x. And what do we see now? Well, we're almost pretty much done because we have in the denominator on the left-hand side, what do we have? P squared, and we have the same usual suspect in the denominators of both summands on the right-hand side, p squared. So if we multiply this equation through, let's write it down here in our time sequence, we multiply this by exactly p squared. What will happen? Gone, 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 and one copy of p goes over here in the numerator. So now we have c times sum of squares, then same exponent e raised to the power p times x, and the same exponent. And then we have p times the trigonometric function of cosine plus q times the trigonometric function of sine. Can we write down the answer for c? Yes, we can. Let's do it over here. So now we have, this is done. Let me grab a new chalk. So now C as a function of P and Q will be what? The one and the same exponent can be safely factored out, so we write it in front. E to the power P times X times what? A certain function that has the shape of a rational function. Now, what do we have in the numerator? We have P times the trigonometric function of cosine times Q evaluated at the argument Q times X plus Q times the trigonometric function of sine evaluated at the argument Q times X. So far, so good. This is the numerator, and what is the denominator? The denominator is the sum of squares. And we all understood the genesis of the sum of squares, right? Q squared over P squared carried over looks like 1 plus Q squared over P squared. Bring it to the common denominator, P squared plus Q squared. So here we have, let's write it down, P squared plus Q squared. So C, of course, to be pedantic, we need to throw in a constant of integration, and again, also pedantically, we need to specify the interval on which the corresponding indefinite integrals are computable. For now, we will omit this, but this is the result. Again, we obtained this result using the scope expansion problem solving approach, and once we know the value of the integral, C as a function of P and Q, what can we do? Well, we can take this C over here, insert it over here, and spell out this expression for the integral S. And I will take another short break over here. I will memorialize this result on top of the board right here, and I will erase the material and make sure that we can bring home the final computation for the integral S. Now that we know the value of the integral C as a function of constant real numbers P and Q shown over here, this is essentially the exponent E raised to the power P times X times the rational function actually in P and Q, P times the trigonometric function of cosine evaluated at the argument Q times X plus Q times the trigonometric function of sine evaluated at the argument Q times X over the sum of squares, P squared plus Q squared, plus, pedantically, plus a constant of integration. I use the uppercase K, the letter uppercase K, so we do not have any collisions with the symbol C. And what remains over here, because this is the equation that we produced during the partial integration of the integral S, all we have to do now is to carry out a finite computation and replace the value of C with the expression shown over here. But just to make sure that we're all on the same page, again, none of this is mathematics with the uppercase M. Just about the only part that was mathematics in this case was the introduction or the generation of an idea or a play of thought to add, perhaps counterintuitively, to the original integral S, yet another integral C. That was the play of thought, that was the generation of idea, that was creativity, ingenuity, or perhaps thinking out of the box, and everything else that transpired after that was not mathematics, that was perhaps computational calisthenics or symbolic shuffling or lesser mathematics, or what happens after mathematics leaves the room. So now all we have to do is complete a kindergarten variety computation. Let's do that together. If you understand what is going on, you can skip forward, or if you did it already, very good. But now here we just basically spell out the value of the integral C shown over here. We omit the constant for now, and we work with this expression over here. So what do we have? 1 over P e to the power p times x times the trigonometric function of sine evaluated at the argument q times x minus q over p times e to the power p times x, and here we have p times the cosine of q times x plus q times the sine evaluated at the argument q times x divided by p squared plus q squared equal, let's bring it over here to the left hand side of your screen. This will be equal. What is going on over here? Well, look at this. We have p in the denominator in the second summand, and we have p in the denominator of the first summand. So this is a common denominator already. What is missing? Well, what is missing is the sum of squares in the denominator here, consequently in the numerator here. So now we basically take that sum of squares and bring it into the numerator. The e to the power p times x and e times x, p times x is one and the same. We factor it out. We carefully write it down over here. E to the power p times x times 1 over p times p squared plus q squared. This is the common denominator. And now what do we have? So now we have the trigonometric function of sine multiplied through by the sum of squares. So let's write down the expression for this. So we'll have p squared times the trigonometric function of sine evaluated at the argument q times x plus q squared times the trigonometric function of sine evaluated at the argument q times x plus what? This is actually, yes, I made a mistake here. This is a minus sign. I'm sorry, this is a minus sign. Minus. So here this will be minus. We have minus over here. I made a typo. This is a minus. So here what do we have? We have q times p. Q times p times the trigonometric function of cosine evaluated at the argument q times x minus q and q squared times the trigonometric function of sine evaluated at argument q times x and the parentheses. So far so good here. I apologize, I was too fast over here. That's not a plus sign, it's a minus sign, because remember when we did integration by parts, minus integral of u dv is u times v minus integral v du. So this is the minus, this is the minus sign. Consequently, this minus sign comes here and comes here, minus minus. Everything looks good so far. Now what do we see? We see q squared times the trigonometric function of sine of this argument with the plus sign, and the same sum with the minus sign. What? Cancel each other out. Wonderful. So now what do we have? P in the denominator, two actually multiplicative copies of p in the numerator, and gone single copy of p over here, 2 copies of p. So let's do this carefully. P canceled in the denominator once, 1 copy of p canceled that is attached to the trigonometric function of sine. This is gone, this is gone. 1 copy attached to the trigonometric function of cosine is gone. And what do we have now? Let's finish this computation here. Let's write it down over here. We will have e to the power p times x. So in the times a ratio of what? P times the trigonometric function of sine evaluated at the argument q times x minus, here is q, times the trigonometric function of cosine evaluated at the argument q times x. This is the numerator. And what is the denominator? The denominator is still one and the same sum of squares. P squared plus q squared, again, plus another constant. let's say this was a constant associated with the sine. This is the constant associated with the cosine. And this is our answer. Again, we understand the genesis of this answer. Every step is shown in a public setting. We saw how this computation unfolds. And again, I will take a short break, erase this material now that we understand where it came from, and I'll write down a similar formula for the integral s, and then we will basically complete our original computation. And now essentially we are done because we know how to express the value of the integral s as a function of the constant real numbers p and q shown over here. I wrote down all the details in their full glory. The answer for the sine integral is shown over here. The constant k relates to the sine, the trigonometric function of sine. And I also wrote down here the expression for the integral that has the cosine, the trigonometric function of cosine in its integrand. Also, the answer is shown over here. The expressions are quite similar, but evidently they're different. And for nitpickers, this is the constant k with the subscript c as it relates to the trigonometric function of cosine. And before we move on and complete this episode and complete the original computation, I just want to say a few words that I plan on having an ongoing series titled One Problem, Many Solutions, because this is the overall approach that is an integral, no pun intended, part of the overall mathematical culture and the mathematical upbringing. We should be able, it is a good pedagogical and intellectual academic exercise to take one problem, fix one problem, and then try to find as many distinct or different solutions to this problem as possible. Or the converse task will be to generate one templatized maybe solution and then try to invent as many problems that can fit this solution template. That's another way to do this, but another way to study mathematics. But along the theme of one problem, many solutions, we'll come back to these two integrals because they can be evaluated in a boring way by using the integration by parts completely all the way through just by working with a single integral. More original idea was shown to you guys over here in this segment, where if we want to evaluate one, we introduce the other, or if we want to evaluate this one integral, we introduce the other, its body, so we evaluate this integral as pairs. And it can also be shown that working, let's say, if we designate this integral with c, then at some point I will show that this relation can be reduced to an ordinary differential equation of order 3. Its shape is shown over here. It has a quite reasonable characteristic equation. This characteristic equation will be of order 3, but it factors quite pleasantly, and the solution of this characteristic equation can be obtained in a straightforward manner. We'll come back to this differential equation at some point. And also, a lot of times students ask the question, why on earth would we want to evaluate these integrals? Well, one answer is that these integrals are quite ubiquitous. They are omnipresent in many different things. For example, we will come back to these integrals when we will be evaluating, for example, this integral over here, the improper Riemann integral that runs from 0 to positive infinity. Here is the shape of the function. Of course, we'll have only one trigonometric function. I wrote it down here in this format to save space, and I will not reveal the entire answer, but one way to evaluate this integral we already saw when we worked with the so-called Fresnel integrals. The same idea of constructing system of differential equations or equations and partial derivatives works over here, and the answer will have something to do with the gamma function. But now that we understand how the integral that has the trigonometric function of sine in its integral is evaluated, we can bring home the original computation. Now that we know the value of the indefinite integral that contains the trigonometric function of sine in the integrand shown over here, we can complete the original computation and solve the original problem S2E30. Here is the original integral, which has as its integrand the product of three functions: the exponential function, the trigonometric function of sine and the trigonometric function of cosine. And we already understand that the value of this indefinite integral is basically the average of two integrals shown over here, where in the first integral, the role of the constant real number q is played by what? By the sum b plus c, b and c being constant real numbers. And in the second integral, the role of the constant real number q is played by the difference b minus c, and the role of the constant real number p in our original problem is played by the constant real number a over here. So consequently, it's a long expression, but we all understand where it came from. The value of this indefinite integral is basically the exponential function, which has the power of a times x, and that function is divided by 2 because we had twice the value of the integral, remember, in our original segment. And in the parentheses, we have essentially the sum of these two integrals of the shape s of p and q. In the first integral, the value or the role of the constant real number q is played by the sum b plus c. So we have a as a factor in front of the trigonometric function of sine, and the argument of that function is what? B plus c, the sum b plus c times x, minus q. Remember this factor over here q, which is the sum b plus c times the trigonometric function of cosine evaluated at which argument? B plus c, the sum, times x, divided by the sum of squares a squared plus b plus c squared. And the second summand will be what? Again, a times the value of the trigonometric function of sine evaluated at where? The difference, b minus c times x, minus, again, q, or b minus c, the difference between b and c, times the value of the trigonometric function of cosine evaluated at which point? At the point b minus c times x, and all this expression is divided by the sum of squares a squared plus b minus c squared, plus, of course, the constant. And pedantically, to make this publishable, we have to say a few words about the interval on which this indefinite integral is valid and for which this formula holds. Now that we understand the maneuver that we executed when we worked with this part of the integrand as a form of generalization, or perhaps the form of analogies but slightly different, what can we do? As an informal homework assignment for you guys to investigate on your own, what will happen if here in this integral we will slug in, let's say, 2 copies of the trigonometric function of sine. In other words, if we multiply this, let's say, by the trigonometric function of sine evaluated at c times x, or if we multiply this argument over here by the trigonometric function of cosine evaluated at b times x. This is for you to investigate on your own, and you know the maneuver that we executed when we evaluated these products. See if you can complete the solution of that problem on your own. Meanwhile, we will move on to a new challenge next. This was the last episode in which we studied the scope expansion or expand and conquer problem solving approach in a dedicated manner. But that does not mean that we should forget all about the problem solving approach. On the contrary, we should incorporate the knowledge of how that problem solving approach works into our daily experience of solving technical problems and use that approach from now onward. And starting with the next episode, we will begin a dedicated study of the so-called elimination problem-solving approach, or eliminate and conquer. If you know how the problem-solving approach works, then by all means use it during the solution of the next challenge. If you do not worry about it. Do your best, and I will explain how does the eliminate and conquer problem-solving approach works in the next episode. But our next challenge will be a mathematical problem S2E30, and the objective of that problem is precisely to use the eliminate and conquer problem-solving approach and to find the radius of a largest circle that passes only through the black squares of a standard 8 by 8 chessboard. And just to make sure, we should not be confusing a circle with a disc. These are two technically different geometric shapes. The circle has 1 degree of freedom, a disc has 2 degrees of freedom. In other words, in order to describe the motion, let's say, of a point mass over a circle, we only need 1 degree, only one variable. For example, the angle is enough. And in order to describe the motion of a point through a disk, we need two variables, the distance from the center and the angle. Here, only the angle with respect to a certain line is enough. So in this problem, we're looking for a circle, not a disk, but a circle that passes only through the black squares of a standard 8x8 chessboard. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you my solution of the mathematical problem S2M33.